I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on conservation of energy examples using energy bar charts to work through a couple problems. So in this video, we're going to talk about conservation of energy, and we're going to look at a couple of examples. We first need to know what the law of conservation of energy is. So in an isolated system, that means the total energy is a constant. So the energy is equal to a constant. Now, the law of conservation of energy is that energy can't be created or destroyed. It just changes forms, changing from one form to another. A good analogy for energy is money. You have a job, you get a paycheck in check form, you deposit in the bank, it becomes electronic funds, maybe you take cash out. It's just continually changing forms until eventually you spend it and you get a product for the money that you spent. Now, the law of conservation of mechanical energy, we've seen this equation in the previous video. The energy conservation equation is all the mechanical energies, kinetic plus potential, plus or minus work is equal to the kinetic plus potentials in the final situation. So remember, you're going to have an initial situation and a final situation, and the work that's done could be transferred in or out. That's the amount of energy transferred into our system. Let's look at an example. So in this example, we have a spring that is compressed a distance, and we have a car that has a mass, and it is launched horizontally by the spring. And we want to write an expression for Vmax, which is the maximum speed that the car reaches after being launched. So step one is to draw an energy bar chart. If you need a review of this, click on the card above and you can learn how to draw your energy bar charts or review how you draw the energy bar charts. So US is the initial situation. The spring transfers energy to the car, giving it kinetic energy. So step one is drawing our energy bar chart. That's complete. Step two, conservation of energy equation. We write our big long equation, and based on our bar chart, we know that there's no kinetic or gravitational. There's no work in the initial situation and no spring or gravitational in the final. So that means our conservation of energy equation that we're going to start with is USI equals KF. So the initial spring energy equals the final kinetic energy. Step three is going to be to substitute the equation for each type of energy remaining. So we talked about the equations in the previous video. So USI and K, so US is equal to 1/2 kx squared, the potential spring energy equation, and kinetic energy is equal to 1/2 mv squared. Step four is we want to substitute the symbols that are given in the problem into our equation. So we're given K as the spring constant, D is the distance the spring is compressed instead of X, MC is the mass, and Vmax is the speed in which the car reaches. And then step five is to solve the equation for what's being asked, in this case, Vmax. So the 1/2s are going to cancel out from each side. So if I divide by MC on each side, take the square root to solve for Vmax, I get the equation Vmax is equal to the square root of K d squared divided by MC. So remember, I like you to solve the equations in terms of symbols first, because it's much easier to find a mistake if you do happen to make one. And at this point, if you have numbers, you go ahead and plug the numbers in and you solve for the value of Vmax. In example 2, we have a box that's sliding down a ramp and compressing a spring, and we want to write an expression for how far that spring is compressed based on the box starting from a height h above the ground. So we know step 1 is to draw an energy bar chart. Energy bar chart, we have gravitational to begin with, spring energy in the final, the earth transferred energy to the box giving it kinetic, and then the box transferred energy to the spring coming to stop compressing that spring. Writing our conservation equation, we write our big long equation, the potential plus kinetic plus or minus work equals potential plus kinetic in the final. So we know we don't have kinetic or spring energy or any work because there's no arrows in or out. That leaves us with an equation of UGI equals USF. So step 3 is to substitute the equations. So UG is mg delta y, US is 1/2 kx squared. Step 4 is we're going to substitute the given values. So look at our diagram, there's our given values. We can substitute MBH for delta y, K and X remain K and X, and we've substituted the variables. So step 5 now is to solve our equation in terms of what we're looking for, in this case, how far the spring is compressed. So I'm going to multiply by 2, divide by k, take the square root of each side, and that gives me the equation x is equal to the square root of 2 times mvg times h divided by k, and this is the expression for our spring compression. And again, at this point, if you have numbers, go ahead and substitute your numbers in and then find the value of the spring compression. Now we're going to take a different approach to this problem. So we're going to use proportionalities to solve this question. So we already have an equation for how far the spring's compressed. And what we want to know is how much higher does it have to be slid down a ramp to compress the spring twice as much. Now you could do exactly the same thing we just did and then substitute in the 2 times x and then figure out how high it's going to have to be. But we have our equation. Now, to use proportionalities, I'm going to get rid of the square root and square each side. And I have the 2 variables that are mentioned in our problem, highlighted in yellow, x and h, which means 2 mbg over k, that's all a constant. Nothing in those numbers or values is going to change. When I have constants, I can remove those constants from the equation, change my equal sign to a proportion sign, and that tells me that x squared is directly proportional to h. So what does this mean? Well, if whatever happens to x, I have to square it, and that's what's going to happen to h. So let's look at it from the equation standpoint. So we know that x squared is equal to 2 mbg h divided by k, but if I double that x to keep this an equation equal, I have to do the same thing to the other side. So if I put the 2 in parentheses, 2 squared is 4, that means the other side has to be 4 times greater. Now, that being 4 times greater, with this being a constant, that means the only thing that can be affected is the height. So that means the height is going to be 4 times greater. So if I double the spring compression, that means the height has to be 4 times greater in order for that to happen. So when it asks us the question, express your answers in terms of h, how many times higher does the box have to slide from? Well, our answer is there in yellow on the right side, 4h. Now, what does it mean for x squared to be proportional h so we don't have to go back to the equation each time? Knowing that the proportion between x and h means if the spring compression x is doubled, the height must be 2 squared or 4 times larger. That also works if we go the other way. If we want the height 4 times higher, how many times further? Well, we take the square root to go the other way to show that the spring compression would be twice as great if the height was 4 times higher. I hope this was helpful in using proportionalities, energy bar charts to write conservation equations and solve for problems. I hope you have a great day and an even better tomorrow.
If you found this video helpful, don't forget to click the like button down below and subscribe to my channel, Cavi Coaches, and follow me on Instagram and Twitter @CaviCoaches.